Hi James, so we've got this parametric integration problem. I've got to be honest, I don't think it's coming up, mainly because they explicitly said parametric differentiation, but nowhere did they say parametric integration. It doesn't strike me as like fair, I guess, to explicitly mention parametric differentiation but not parametric integration. But the secret is you're going to integrate y dx by dt with the limits in terms of t. That's essentially how you do parametric integration. And I'll quite happily work through this question to show you. So given that the point P lies on C and has parameter pi over 3, I'm going to find the coordinates of P. So we've got x equals 8 cos of pi over 3. Well, that's cos of 60, which is a half. And if you cube it, you get an eighth. So the x coordinate seems to be 1. And the y coordinate, well, if we do sine of 60, that's root 3 over 2. Sine of pi over 3 is root 3 over 2. Square it, you're going to get 3 over 4. Times it by 6, well, 3/4 of 6 is 4.5. And so we get 1, 4.5 for P. Yeah. Now the line L is normal to C at P. Yeah. So we've got to show that that's the equation. Well, okay, this is parametric differentiation, and this definitely is coming up in paper too. So let's do it. Dx by d theta is going to be 24 cos squared theta, but then you've got to remember you need to differentiate the cos theta, so minus sine theta. And then dy by d theta is similarly going to be 12 sine theta cos theta. And so if I want the gradient of the tangent, I'm going to use dy by d theta divided by dx by d theta. Now, it might look hideous, but remember, we're just plugging in pi over 3, yeah? So if we plug in pi over 3, we're going to get sine of pi over 3. Let me give myself a little bit more space. I'm going to get dx by d theta equals, okay, cos of pi over 3 is cos of 60, which is a half. Squared is a quarter. 24 times a quarter is 6. So I'm going to be doing 6 times minus root 3 over 2. And I believe that's minus 3 root 3. I think. I'm just going to write that down over here. 6 times minus root 3 over 2. Does that look right? Yeah, that looks right. Okay. dy by d theta is going to be 12 times sine of pi over 3 cos pi over 3. Well, sine of 60 is root 3 over 2, so times it by 12, you're going to get 6 root 3, and you're going to be multiplying that by cos of pi over 3, cos of 60 is a half, and so we're going to get 3 root 3 for that. So interestingly, we end up with the gradient of the tangent would be that divided by that, which would be minus 1, and therefore the gradient of the normal is 1. So we've got y equals x plus c. Now we just need to plug in a point on the line. Well, the nice thing is we've got this point, 1, 4.5 up here, and so we're going to get 4.5 equals 1 plus c. So c is 3.5, and somewhat satisfyingly, we get y equals x plus 3.5 for part B. Okay, right. Now we got to find a region of parametric integration. Now you really want to break these up because if you integrate, well, we could integrate under the line from here to here, but that's just a, what do you call it? Trapezium, yeah? Where this is 3.5 and that side is 4.5. So let me just explain the 4 that they get at the start of this formula, because I've got a little 4 kicking around there. I'm guessing that that comes from the area of the trapezium, yeah? So the area of the trapezium, area of trap, is going to be h over 2a plus b. Your a here is 3.5 and your b is 4.5, which add to give 8, and your h is 1. So we have a half times by 8, which is 4. Yeah. Now we need to integrate this curve from there down to there. Now, the easiest way of doing that is to use a parametric integration formula. So let's do it. The parametric integration formula says we need to integrate y, which is 6 sine squared theta, multiplied by dx by d theta. Now we've already worked that out. Dx by d theta is all of that there. So we're going to be timesing that by 24, well, minus 24 cos squared theta sine theta. With respect to theta, now what are our limits? The limits must be in terms of t as well. And we know, or theta, sorry, I should say. And we know that theta is pi over 3 there. and it's going to come down to have a theta value here. Well, that's going to be where y is 0, and y is 0 when theta is 0, yeah? Because you've got 0 equals 6 sine squared theta, and therefore theta is 0 there, yeah? So that's what I'm going to actually be integrating. And they need to show me, they're asking me to show that it's the same as that. Well, the good news is that 6 times 24 is the same as 12 times 12, and so that is 144. The minus can actually flip the limits round, and so that's what I'm actually going to do, and that's from a clever trick which I've mentioned before, where the negative of AB f of x dx equals the positive of BA f of x dx. It's a neat little trick you can do with the limits there. Okay, and then we're going to have here, well, if we look at what we've done 6 times 24 and taken it outside. We're going to have sine cubed theta, cos squared theta. Now, I'm looking at that. Oh, yeah, it was y times by dx by d theta, wasn't it? So I'm just checking I've got everything there. There's a y, there's the dx by d theta, and we're integrating with respect to theta. Now, if we look at this, they've got a cos squared and a cos to the power of 4 and just a single sine theta. So maybe we should write our sine cubed theta as sine squared theta times by sine theta. Then I can write that as 1 minus cos squared theta. So that's my sine squared. Cos squared theta d theta between 0 and pi over 3. What a horrible question. And that's going to be, now we've got it basically, sine theta cos squared theta. But then when you times that by the last term, you're going to get minus sine theta cos to the 4 theta. And I know why they've got us to write it in that format. It's because now both those terms can be integrated using f dash of x, f of x to the n dx. That formula comes up a lot, and it's f of x to the n plus 1 over n plus 1. But like I say, I really don't think they're going to give you parametric integration. They could give you integration like this, though, and that's why I never mind going through things like this, because once you know the formula for parametric integration, the difficult bit is not knowing that formula. The difficult bit is integrating the fiddly trig functions. And so that's why they've got 4 plus all of this. That's the area of S. Hence, find the area of S. Okay, right, I can now integrate it. So with the plus 4, you're going to get 4 plus 144. I can actually integrate that now because that's the, well, it's almost the derivative of that. I'll need to make this minus cos cubed theta over 3. And then cos theta differentiates to minus sine theta. This is going to become plus cos to the 5 theta over 5 with those limits pi over 3 and 0. And then do check this on a calculator, but I'm going to get cos of 60, well, that's a half cubed is 1/8 divided by 3 minus 1 over 24 plus, we're going to get a half to the power of 5, which is 1 over 32 times 5 is 1 over 160, I think. It's 32 divided by, yeah, because you're going to get 1 over 32 divided by 5, times it by 10 and halve it, so 1 over 160. Always plug in the 0 carefully, because when you do cos of 0, you get 1, so you're going to get minus a third, plus cos of 0 is 1 as well, plus a fifth. And then we're going to do all of that, so we got, watch me just faff about with these fractions. Now, I think actually, where's my calculator? Let me just quickly find my calculator. 1 divided by 160 minus 1 divided by 24 minus open brackets 1 divided by 5 minus 1 divided by 3. Okay, I'm getting 47 over 480 in there at least. And so I think the final answer should be times by 144 plus 4. 181 over 10. Yeah. Do let me know, though, if that's wrong and I've made a mistake. I'm kind of rushing through things at the moment because I've got a lot of questions to go through. But I hope that's helped, James. Best of luck with the exam on Tuesday. I'll be in school tomorrow, so if you need to pop in and ask me anything, please do. Bye-bye.